Uh, all right, so I'm Robert, and I'm happy to be here today to talk about our work on cache side channel detection with our tool CaSym. So to start, I'd like to go over at a high level how cache-based side channels work. So if we imagine that we have a program here, and the program is going to take some sensitive data as input, and as we process the data, it's going to leave some artifacts that may be observable in the CPU cache. So the adversary can extract these artifacts maybe using a prime and probe or a flush and reload style attack. And then if we imagine a program that takes the same program with the same public inputs but a different sensitive input, and it also processes the data and the final cache state is different, the implication is that there's information flowing from the sensitive data into the cache, and that's the unintentional information transfer that's happening. So just how severe is this problem? These attacks have been shown to be rather high bandwidth, so there's been work that's shown that they can get up to over 100 kilobytes of leakage per second. They've been shown to work on secure enclaves such as Intel SGX, and they've also been shown to be able to be launched across cores across virtual machines in the cloud using the shared last level cache. And most recently, the Spectre and Meltdown vulnerabilities have brought these side channels to the forefront, taking advantage of speculative and out-of-order execution to leak arbitrary data from the victim address space. And one of the main problems is finding these vulnerabilities in code is often quite challenging because microarchitectural properties are often quite subtle and hard for people to think about as they're programming. So there's been some prior work on this. So one of the first ones would be a cache audit that was from 2013 from Usnip Security. And what they do is they use abstract interpretation to try and relate a program execution to how the cache behaves. And they try to compute an upper bound on the leakage from the source code via the cache-based side channel, but they don't provide any information to the programmer on where the vulnerability is in their program. And then more recently, in 2017, a tool called CaSym uses symbolic execution to build the relationship of how a program executes in the cache state. And they're able to detect where the leakage happens, but they may miss side channels because they require some inputs to be concrete, which means it may not go down certain control flow paths that actually have vulnerabilities, and they don't provide any way to fix them. So because of these two limitations, they're also not able to verify that programs are actually side channel free. So that's where our work comes in. So we propose using cache-aware symbolic execution. So we're able to soundly model cache-based side channels, so those resulting from memory accesses where the memory address is computed from some sensitive data, and also branches where the condition is tainted and the different branches will access different data. And we're able to detect where the side channel happens in the code so we can identify the line of source code that causes the vulnerability and tell the programmer why it happens. And we're able to provide some simple fixes to remove the program and then verify the absence of the side channel. We also include a variety of different cache models that yield different precision and efficiency. So as an overview, our tool takes as input a C source program and uses the Clang compiler to generate LLVM IR code. We then perform our analysis on the LLVM IR code, and we will require a model, and the model is going to include an attack model and a cache model. We'll then generate a verification condition, which will be passed on to the Z3 SMT solver. And if the SMT solver reports an unsatisfiable result, that means that there's no cache-based side channel with respect to the models that were used. And if it's satisfiable, we'll generate a localization report, and the localization report will tell the user why the side channel happened and where it happened. And with that information, the mitigations can be applied, and then if the user wants to verify the absence of the side channel, they can run it back through our tool, and if it reports unsatisfiable, it means that there's no side channel. So to kind of go over an illustrative example, we talk about the square multiply algorithm, which is used in modular exponentiation. So this is commonly used in asymmetric cryptography. So in these cases, the exponent is typically the private key, and here the loop is going to iterate over every bit of the key. And when you see on line 6 that there's a key-dependent branch, and inside of the branch it's going to access some data that wouldn't be accessed if the branch wasn't taken. And this is going to leave some observable remnants in the cache that can be exploited by an adversary to learn information about the key. So our tool uses a symbolic execution. So unlike some tools that use a symbolic execution, we actually treat all program variables as symbolic values instead of making some of them concrete. So this is true for both public and private inputs. And then we also introduce cache variables, and we're going to create a cache variable for every public variable. And these cache variables are going to be expressed differently depending on which cache model is selected. So the verification step is going to require us to take a program, and essentially we start off with the original program, and then we're going to duplicate the program, renaming all of the variables, so we're going to run the program twice. And initially, all of the public variables and the cache variables are going to be equal, and only the sensitive data will be different, so the SMT solver will be able to select two different values for the private data. And what we want to see is, at the end, are there two different possible cache states that these sensitive data can cause. And in the event that the cache variables are not equal, that means that the cache states are different, and we'll report a side channel. And if they're always equal for any two possible key pairs, that means that there's no information flowing from the sensitive input into the final observable cache state. So the reason we use these cache models to abstract away some of the details is oftentimes caches are rather complex, so the cache hierarchies, replacement policy, inclusivity, and a lot of these properties vary tremendously, and a lot of times they're not even available to us. A lot of the details are kept private. And even if they were known, they vary amongst many architectures anyways. So we developed these models to be apply more generally. So our infinite model is a rather simple model and an under approximation of a lot of real behavior, and treats cache as if it's an infinite set. But we find that even though it's simple, it actually is pretty good at finding side channels. And then we have our age model, which over approximates real policies by essentially keeping track of how old each variable is. So essentially the age is how many accesses have passed since it was last used. And then we have a more realistic model called a least recently used model, which also uses an age, but it essentially, the expression is going to be a binary result, which is either it's cached or it's not cached. So to demonstrate how these models would work, we have this toy program here, and we're going to initialize the cache to be all false. And then when we execute the if condition here, we're going to access the key, so we'll mark that as true. And then you'll note that the key value here is assigned to be 1, so we'll go down to the then branch, and we'll get A as access, and we'll get true. And then on the second execution, the SMT solver might select 0 to be the key value, and we'll still execute the condition, and this time we'll go down the else branch, and we can see that there's going to be a difference in the final cache states, and this is what our tool is looking for. And then to demonstrate how the age model might work, so here we start off with all of the ages to be infinity, which means that they haven't been accessed yet, essentially. Then when we access key, initially we'll increment all of the ages, and here incrementing infinity by 1 is still infinity, so they stay the same. And then since we access key, we'll set that age to 0. And then again, when we get to the line in the then branch, we'll increment the ages first, and then we'll set the program, the cache variable that was used to 0. And then when we go down the else branch, it'll be very similar. We'll do the increment and then do the access. And at the end, this model will actually provide essentially a sequence, an order of the memory access pattern. And we can see that with the age model, it'll also report that there's a side channel in this program. So we had to make some trade-offs to improve performance because symbolic execution is typically rather an expensive process. So the array reads, when we read from arrays, are going to be unconstrained. So when we drop the constraints, that essentially will treat them as private variables. So in order to overcome this, we use a taint analysis to be able to tell if they're sensitive or insensitive. And then we have this reset command, which is going to reset the constraints. So it essentially allows us to break a program up into multiple components and verify the individual components. And we also apply this taint analysis to make sure that when we drop these constraints, that we still know which variables are sensitive and insensitive after a reset. And this command is particularly useful when we go to reason about loops. So we also have a loop transformation that will soundly rewrite programs to be loop-free by using our reset command. And it makes it very convenient because then we don't have to unroll loops. And when you do loop unrolling in symbolic execution, it typically causes a path explosion. It was difficult to get performance. So more information about this details can be found in the paper. So now to briefly talk about the two different attack models that we consider. So in the access model, essentially an adversary is able to observe before and after some window. And they're able to see a sequence of memory, or a set of addresses that are accessed, but they can't see the sequence. They can't tell the order in which the data is accessed. And then a much stronger attack model is a trace-based model where they're actually able to see after every single memory access. So they're able to get a sequence of memory addresses that are used by the victim. So as far as results, so here I'll talk about our crypto results for using our trace model. So using our infinite model, we're able to identify 269 unique vulnerable points in these benchmarks in about 200 seconds, which is quite good considering that the infinite model is actually an under approximation. And then we have our age model, which is able to identify one more vulnerable location. And the trade-off here is that it takes an order of magnitude more time to execute. And then our most realistic model actually more closely corresponds to our infinite model, which highlights actually how effective our more simple model is at finding these vulnerabilities, but it'll still actually take a significant amount more time. So the one benchmark where we see a difference here is going to be in the square and always multiply routine. And the only reason the age model still reports a difference is that the order of the accesses is still different. And the LRU model doesn't report anything because the difference is actually very close together. So it's only a couple of memory accesses apart, so they're actually both going to be cached, and it's going to be indistinguishable. And our infinite model reports the same as our LRU model. So we're also able to verify the absence of side channels, so we introduced two primitives, preloading and pinning. So preloading, the data is going to be cached at the beginning of the function. And with pinning, it's going to be cached throughout the function. So when we analyze the program, we see that with the infinite model, it reports that there's no side channels because things will never be evicted from the cache with that model. So if it's preloaded at the beginning, it'll be permanently in the cache. And with the age model, we still report side channels because the order of the accesses remains unchanged. And then pinning, the data is going to be cached throughout the function. So what that means is that the age that we use for the age model is always going to be 0 for those sensitive values, so it won't ever change. So we're able to verify the absence of side channels in those crypto benchmarks with these defenses. So in conclusion, we build our tool CaSym to automatically identify vulnerabilities in programs. And we're able to support a variety of cache models that will deliver differing amounts of precision and efficiency. And we tested on an assortment of benchmarks. We confirmed existing vulnerabilities in crypto code. We verified the mitigation strategies on some of the crypto benchmarks. And we found over 20 new vulnerabilities in the Postgre SQL database, which I didn't have a chance to talk about today, but you can find that information in the paper. So thank you.
Hi, Stefan van Schaik from VUSEC. So I see it's interesting work and great talk, by the way.
Thank you.
So I see you simplified the model for accessing addresses, but have you considered confused deputy attacks where you have a benign component in your CPU that you can mislead to do cache attacks for you? An example of this was previous year at Usenix, translate attacks or malicious management unit, why stopping cache attacks is harder in software than you think. So how are you planning to actually address these kind of issues?
I'm not sure exactly. Can you explain more details what you're referencing?
Yeah, so what the paper showed back then was that you can use the memory management unit just by accessing addresses to get page tables in the cache to still perform a cache attack.
Yeah, so we don't consider the page tables in this model, but so one of the nice things is that we can still apply the base symbolic execution to, as we just need to formalize how that model would work. So in our cache model, if we included that with it, it would be able to reason about that, but that's not something that we considered.
Okay, thanks.
Thank you.
Hi. So network. So you initialize all the global variables as symbolic values. Some of those variables as pointers. How do you handle symbolize the pointers?
So for pointers, we actually have to simplify them a bit. So we typically, once we have to, we only allow them to point to essentially one data structure at a time. So if they point to a different data structure, we don't verify the program, but that didn't happen in any of our benchmarks. But we can reason about like pointer arithmetic as long as it points to one memory region, so one array at a time. That will be verified.
Have you thought about like finite maps, those kind of techniques you handle?
No.
Okay, thanks.
All right, thanks.
Any more questions? We still have some time left here. Well, maybe then let me ask a very quick question here. For the 3 cache models you constructed, are they generically applicable to different architectures or different processor families?
Yeah, so that's why we wanted to have these abstract models, is so we don't make any assumptions about how the architecture works, so they are applicable to multiple architectures.
Right. Thank you. Let's thank the speaker one more time.
Thank you.